Bismillahirrahmanirrahim. In today's video of network analysis, we'll be solving end chapter question 12.31, and this is on the request of a student. So let's see. This is the question. A balanced delta connected load is supplied by a 60 Hz three-phase source with a line voltage of 240 volt. Each load phase draws 6 kilowatt at a lagging power factor of 0.8. We have to find these three parameters. First of all, let's understand what does it mean, what is the definition means. When it says the delta connected load, so it should be something like this, delta connected load. It is also saying that each load phase draws 6 kilowatt, so the power drawn by the load is 6 kilowatt. And each phase has a power factor of 0.8 lagging. That means this is inductive load. Also, the line voltage is 240 volts. So this between line to line, actually line voltage is line to line voltage. So this is 240 volt. And now we have to find the load impedance per phase. So the value of this impedance per phase we have to find. So these are some of the formulas that we have learned, and we'll be using these. These are all for per phase. Also, this formula can be summarized everything. Now there S is the total complex power, which is actually 3 times the per phase complex power. This is P is for phase, so per phase complex power. And these are various formulas that we have learned. What we are interested is in this formula. The impedance we have to find ZP. Also, there's another way of defining the complex power, that is it as P plus JQ. Now, if you look at this diagram, this is the real axis P, this is imaginary axis JQ, and the sum of the two is S equals P plus JQ, and that is why it is complex power, because this has a J in it. And if we just consider the magnitude, then it is called apparent power. This is just for your knowledge. We'll not be using it here. And this can also be written in terms of under root 3 VL/IL and the angle between and the impedance angle, we can say, or angle between voltage and current, theta. So the first question is the load impedance per phase. Now, to find load impedance or Z per phase, we need to find S, that is the total complex power. Now this, so to find ZP, we need to find S. Now, while we are writing in the book, they have printed it bold, but while writing, we can just put a bar on top, so that will show that this is complex power. And we have also learned that the complex power, total complex power, is 3 times the per phase complex power. And per phase complex power we just learned is P plus JQ, or P per phase, or the real power per phase, plus JQP, that is the imaginary power per phase. And given in the question is that each load is 6 kilowatt, that is 6,000 watts. So PP is given. And we have to find QP to find SP, and from there we can go back to S, and from there we can find ZP. Now, the real and imaginary axis can also be written as PP is SP, that is the complex power multiplied by cosine theta. I hope you remember the formula for sine and cosine. base divided by hypotenuse. So this is and perpendicular divided by hypotenuse. Okay, now from here, if we need to find SP, because this both the terms are given, we will find SP, and using SP in this, we'll find QP. Let's see. To find QP, we need SP and theta. And SP can be found from here, which is SP is PP divided by cos theta. Now per phase power is given 6000 watt or 6 kVA. Cosine theta is the power factor, 0.8 given. So SP in kVA becomes 7.5 kilovolt ampere. Also, from the cosine theta is 0.8, we can find the angle theta, which is 36.87, taking cosine inverse of 0.8. So we have found SP, we have found theta, then we'll find QP. So QP is SP sine theta, 7.5 kVA, sine of the angle. And for Q, which is a reactive element, instead of kVA, we'll write kVA R for reactive, just to distinguish that this is reactive power. And so solving this, you can get 4.5 kilovolt ampere reactive. Okay, so now that we have found Q and P, we can find per phase complex power. This one is 6, this one is 4.5, all in kV. And from here, now we'll find ZP. Okay, now to find ZP, we need to find the total complex power. We have found it. Complex power for one phase. So total complex power will be 3 times the complex power per phase. So 3 times this value. So this is the total complex power. Okay. So total complex power we have found. We will use this formula now. This was the formula that we are discussing. From here, ZP conjugate will be 3Vp square over S. S we have found. Vp also the per phase voltage. Vp is equal to V line is equal to 240 RMS. From here you can see the phase voltage, that is voltage across any one phase, is also equal to line voltage in case of a delta. And so this is 240. So Vp is 240. So plugging in the values, this is 243, this value 18 plus J13, and for kVA we multiply by 10 raised to the power 3. Solving, we get this answer 6.144 minus J4.608. Now remember, this is ZP conjugate. We have to find ZP. And I hope you know that the difference between ZP and ZP conjugate is the sign. We just need to change this sign. ZP will be same value, changing this sign from negative to positive, and this value in ohms. So this is the answer of part A. Now part B is simple. We have learned this formula, and PP we know, VL we know, so theta we know, therefore IL we can calculate from here. Theta is the angle of the load impedance, or also it is the angle between phase voltage and phase current. So from here, IL will be PP over under root 3 VL cos. Putting all the values, VL 240, 0.8, so 18.4 ampere. Now part C is slightly tricky. Okay, now we have to add capacitance here. I hope you know that the capacitance are added to improve the power factor. Now here the condition is find the value of the capacitance needed to be connected in parallel with each load to minimize the current from the source. So how do we minimize and what does it mean to minimize the current from the source? So let's see this diagram. This is voltage and this is current, and the angle is theta between them. Now IL will be minimum when theta is 0. That means when we bring it up to this point, then when theta will be 0, this will be the smallest value of IL. And when theta is 0, the power factor will be 1. Another way of looking at we just because there will be another theta, so I'm just changing this theta to theta 1. And then for our ease, if I reverse this, if this goes up, and let's say I call this voltage as 220, then trigonometrically also we can calculate the value of IL. Now, as I was mentioning, that cosine theta is base over hypotenuse. So 220 over IL, or IL1 we are calling it. And let's say it is 45 degrees, just to give an example. So IL will be 311. Now, if we reduce this to 0, then what will happen? So IL2 will be 220 cosine 0, and this is 220 ampere instead of 311 ampere. So this is the minimum possible value. So minimum possible value is obtained when cosine theta is 0 or power factor is 1. Okay, now what does the capacitance do? Capacitance, when we connect it in parallel, the inductor is pulling the current down, current is lagging, and the inductor is pulling the current up, that is, current is leading. And if these two angles are equal, then we'll have 0 angle for the current. This another way we can look at it is with this power triangle. This is the real power, this is our imaginary power, and this is the complex power. Now what we want to minimize this Q. This has to be 0. That means since QP is 4.5 kVAR, this value we have calculated it 4.5 kVAR. Therefore, our capacitor should pull it down to 0. That means QP should be equal to QC. This one, bring it down, so the value should be same. So we can say that QC should be equal to QP, which is 4.5 kVA or 4500 VA. Okay, now QC known, we have learned this formula from chapter 11, that the value of C can be calculated from this formula, QC divided by omega V RMS square. And so putting the value, this is 4500, omega is 2 pi f, frequency is 60 hertz given, and 240 is the line voltage or RMS voltage, so square of it. Solving, we get 2.072 10 raised to the power 4 farad, and which can be written as 207.2 microfarad. So I hope you have been able to follow this. Please let me know through your comments. Thank you.